So yeah, thank you for the introduction, Marcus. A little bit for the setup. So as Marcus said, I'm a coordinator of Area C. That is the area in FAIRmat that deals with theory and computation, hence the title. And I'm going to talk, essentially do a little bit of a step back with a slight bit of history and to explain this parenthesis metadata and a little bit how things were built from the beginning. So as Claudia has mentioned in her introduction, Nomad started with the theory data. So I will show a little bit some of the in some sense old stuff that is working since a while on the Nomad infrastructure. So very briefly, the area deals with theory and computation, and more specifically, we have different sub areas or tasks about ground state calculations, MD simulations, and multi-scale modeling, and excited state kind of modeling, and loosely speaking, in the kind of time length scale, the three areas span a little bit what we can do in theory. Okay, there could be something above here with continuum and thermodynamic models, but not there so far. Yeah, so this is everything I will say about the area structurally, but I thought it was good to introduce the area itself, besides the work behind, and same slide, but now with names of the leaders and the domain experts that are working in the area. As I said, I want to do a little bit of step back and start from the original formulation of FAIR data from the Wilkinson et al. Paper in 2016. So the findable, accessible, interoperable, and reusable paradigm that after many discussions, so the R can be reinterpreted in other ways, because maybe reusable is not understandable enough. But then I will add another one that actually was already hinted by Claudia in her introduction. And so slide fast forward to 2019, when in this very room, in the year one before COVID, we gathered and we had a lively workshop. So before FAIRmat was funded, and one of the topics was to understand what actually are metadata in the scientific context. And so we had a discussion starting back then in July 2019, and after a lot of back and forth, it ended up with a paper that is not yet peer-reviewed published. So this is the archive version, but I'm working on the review after the referee reply. So the paper will be out relatively soon. And just to show that a contributor of this paper, many of them are today in FAIRmat. Some of them are not anymore in FAIRmat, but we are really spanning a lot of the material science, mainly computation. No, this is more than computation, sorry. It is the material science community. So what we ended up was a kind of discussion in which we define, first of all, data objects, also called information resources, that they have to be considered as a complex object that has attributes. So one can imagine a data object as something that can be represented in a table, in a table kind of representation, and the attributes are the columns of this table. And then imagine that a data object is something about some calculation that has some identifier, and then has been done on certain structure that with the suggestive name is called graphite.xyz. And then somebody has done a calculation with some method, and then some some observable is calculated. And so the point here I want to make is that the attributes of these data objects are data or metadata depending on the context. So if one does a calculation, one can say that the data, what has been calculated, is this observable, maybe a new structure that depends in some sense on the input structure, and the metadata are what led to that observable and new structure that is the input and the method. But this new structure could be the input to the next step, so that becomes data now, and then the metadata would be, so it becomes metadata and the data would be something else. This is in addition to other metadata that are maybe the more common metadata in data science. So the administrative one, this is who did the calculation, who can access the data somewhere, and so on. So all this together contribute to be the metadata, and this is what we capture in the, let's say, in the Nomad infrastructure. And also already essentially in this simple table representation, one would like to know everything that contributed to arrive at a certain piece of data. So the so-called provenance. So well, to arrive at the definition, that was what we proposed in the paper, is the attributes that are necessary to locate, fully characterize, and ultimately reproduce are the attributes that are identified as data. This is the metadata. And then the metadata include a clear and ambiguous description of the data and their full provenance. So of course, these are by themselves a little bit empty words, unless one contextualize them in the actual implementation, because the unambiguous description is the kind of biggest challenge that one has enough information to characterize in an unambiguous way the data. And so this has been implemented, this idea in the Nomad infrastructure, that for what concerns the Turing computation data is in a sense has always been a little bit simplified by the fact that people run simulation by running codes. These codes are already in a computer or run in a computer, and so one has input and output in a digital format. So from the very beginning, we started saying, okay, give us your input, your output, and some specification on the codes, and this is what we store in the so-called repository. That is the, in some sense, the raw data. And then these data are processed and transformed into the Nomad archive by means of the metadata representation that I'm going to quickly explain, so that for once you see also a little bit the reasoning behind the determination of the metadata structure. And after the data are in the archive, they can be accessed via an API. I will show a small example at the end, and processed by notebooks or the browser, the GUI that you have already seen a bit in these talks. So the repository started in 2014, so before the FAIR paradigm was published, and so we were ante litteram FAIR. And the repository has an enormous amount of data, depending on how you count them, 100 million entries or 10 million different calculations. Thanks mainly to the contribution from the big US repositories or databases, so Aflo, OQMD, and Materials Project, because the in computation material science, people started, say, from the early 2010s storing a huge amount of data, and all of these repository are growing even at a fast rate, and to some extent we have a synchronization with them in the Nomad archive. Yeah, so this is a snapshot. I still like the graphic of this one, even though the numbers are a little bit older, of the different codes that are represented into the Nomad archive. So from the point of view of computational material science, life is easy, because when you have a calculation, and in particular you deal with an atomic simulation code, you have to specify which code was used and which version of the code was used. And then you have different kind of inputs. Typically, you can separate them in information about the structure of the system that you are simulating, and the physical model. One can further split this input part in the kind of ideal physical model and its numerical implementation. At the moment, this is together, but with more recent work, we tend to split these two concepts, because there is a concept of physical model might be implemented differently in different contexts. And then you have outputs. Therefore, in our metadata representation, we have all these things mapped in a structured way, so that when we look for the result of some calculation, we access what kind of input was used in a structured and unambiguous way. And okay, so this structure is kind of mirrored in our representation in the Nomad infrastructure. So if you go to the main Nomad Lab page and go to calculations, you are presented with, well, actually this is not the first thing you will find. You have to go to the meta info browser. So these are our metadata. And then you could find all these things that I've been showing, among many others, but I wanted to highlight the main concept. So we have method, system, and calculation. That is exactly what I've shown in the previous slide. And then if you follow the rabbit hole, you find information about the atoms and so on and so forth. And in general, this is can be summarized by saying that again, you have this information about the output. So in some sense, the data and the metadata are connected to the output by referencing to them, so that you can find all the pieces of information that you need. Okay, summarizing before I go to the little bit of live demonstration, semi-live demonstration, is that in terms of fairness, the theory and computation is doing quite well. So the data are findable, are accessible, and then via this extensible schema, they are interoperable and to some extent reusable. The nice thing is that these data are artificial intelligence ready, that if you see this AI R can be also plugged into the FAIR acronym, so it's also a way to remember that data should be AI ready. Well, before that, I want to go to the demo. So essentially, again, if one goes to the main hub of the Nomad laboratory, now you would be presented with a kind of a browser page, and I will do a very random, not prepared before search, in which I look for calculations that are done with the VASP code, and then they have been calculated with some GGA functional. For some reason, I am interested only in cubic symmetries, and also in materials that contain oxygen and are ternaries. And then every time I do a thing, so I decide for a filter, dynamically the results are scaled down. I don't know if you can see this number, but we started with the millions and now we are going to 65,000. And then I want to look for geometry optimized result within a certain threshold. So all these things can be done, so are done live. I'm brave enough. And then you get a lot of results. So 8,000 something. And if we look at their origin, in very unexpected way, they are distributed between materials projects, A-flow, and OQMD calculations. And then, okay, I'm happy about this query, maybe, and then I can take out the code, the Python code that I can directly use in a notebook. That is what I'm showing in a second. So again, from the main hub here, you can go to the toolkit tool, and then yeah, probably the page will change, but still this will be findable. And then you would, if you go to this notebook query the archive, in a very, very random way, you find exactly the same search already prepared that gives exactly 8,862 results. But what I want to show is that this search is across different databases. So, I mean, they are in the NOMA database. They were calculated by different people, different groups with different purposes. And then for some reason, we were interested in ternary oxide materials. At the front of the notebook, one uploads all the Pythonish things with the artificial intelligence kind of libraries, and here would be the nomad part that is important, because then you can query the archive and get your output. Then at some point, some magic happens when you prepare your data frame. I skip on this. Of course, it's the main part of the notebook. But once the data are in your data frame, you can look at some statistical analysis of your data, like a distribution of atomic density. And then here, what we did, by the way, so this is live. You can go there the moment you access the web page. And so what we did here is unsupervised learning on this data. So basically, we did a clustering analysis. So we wanted to look if these data points are represented by means of some information of the atoms that constitute the material. So there is a kind of 8-dimensional, I think, or 7-dimensional representation of each material. And we wanted to see if there was a structure in this 7-dimensional representation. So you do what is called clustering in artificial intelligence, unsupervised learning, and then a projection into 2-dimension. And yes, indeed, the algorithm found a nice clustering between two subsets. Here, the outliers are not represented. You can switch on and off. But this is all, say, yeah, reactive. And then you can just look at the structures. So what it is doing when I click this button is that the notebook is going back to the archive and pull out the structure in terms of coordinates, and then you can visualize it and do some further analysis in your notebook. And then here there is some analysis of the different groups. You discovered that one of them is essentially one type of space group within the cubic family, and the other one is mostly another type of space group. Not very surprising, but just to say that, yeah, okay, you can visualize this kind of things in a nice way. And the next part would be some kind of supervised learning. So with a random forest, we try to predict the atomic density as a function of just the composition. And this would be a result example in which it says that, yeah, the prediction, including the spread, so we are learning both the average and the spread of the distribution, So basically, you have a ternary material. We run over all the second element and fix the first element, and then we discovered that the atomic density has mirrors the structure of the shell structure in the periodic table. So this was kind of a little bit of a finding after this analysis. That is again done on data that are in the repository. Nobody meant to do this analysis on this data, and they are there, and you can redo it, change the observable, and report. And of course, then this notebook is there and stored. But then whatever you do, you can store it yourself, share it, and you have everything is reproducible because you have exactly the query on the archive and your analysis. I guess I have to close, right? I think I started late. I don't think it was so slow, but anyway, I'm ready to close now with the. Yes, so we have many activities going on, but I really wanted to spend time on the things that are already there and working, and so there is something happening. I don't go into the detail now, but I want to leave the acknowledgement of what you have seen now is thanks to the people that you see listed there, and I thank you for your attention.
Thank you, Luca.